So, all right. So, what the plan for this coming Friday is that we have a visitor from Abacus who is going to give a lecture on some of the advanced capabilities in Abacus, like nonlinear analyses, and some fluid structure interaction, and some nifty applications. So that lecture is going to be in ARMS, Armstrong Building, the same room as the exam, B061, same time. So next lecture is there. And since he's going to talk about some nonlinear methods and perhaps some dynamic methods also, um, so I thought that maybe I'll give you a very brief overview of some of the topics about dynamics and nonlinear problems. And this might come in handy for you in your term project also. Uh, since we have not really talked about nonlinear problems or dynamic problems, ideally I would suggest that you don't try to attempt something too complicated, but just so try to get some of your simplest models working first, and then if you get time, or if you get or if you're enthusiastic about trying some nonlinear problems, then uh, you can try to see how to do that in Abacus. So in order to do those kinds of problems, I think you'll need some background about what's going on behind these dynamic and nonlinear problems. So let's see. All right, so let me first discuss something about dynamics. So we already know that the governing equation that we talked about in statics was this div sigma plus b is equal to 0. But in dynamics, all that we have is rho u double dot. And you know where this comes from. If you draw a small cube in the deformed configuration, and you write out the sum of forces is equal to mass times acceleration instead of sum of forces equal to 0, you will get this. Okay, so that's just the Newton's second law. Sum of forces, if it is not equal to 0, it's equal to mass times acceleration. So that you will, this governing equation for dynamics holds for three-dimensional, two-dimensional objects. And this holds point-wise, which means that any point anywhere in the domain you go, this equation must hold. So similarly, in addition to the domain equation, you have the boundary conditions. The first boundary condition is that the displacement on the specified edge, so this is the specified boundary, the displacement has to be specified here. In general, if it is a fixed boundary, we say that displacement here is 0. So this u naught in general could be some complicated function also, or it could be just 0. So for example, if you have an earthquake, when you supply ground motion, that's you're supplying some ground motion to the boundary. So what you could do is approximate this function with whatever ground motion was measured for earthquake problems. And I think there is some trouble with this. You can delete. I don't know where this came from. So there is this second boundary condition on the force or tractions. So the traction boundary condition says that this on the part of the boundary that is free, you need to specify the tractions. So for example, if you have this kind of a cantilever domain and you drop a ball on that, this is clearly a dynamic problem. The ball hits here, and then the beam might oscillate up and down, and that wave might propagate along the length of the beam. So that's the kind of dynamic problem that you could be solving. So obviously you can see that the solution u, displacement at each and every point in the beam, that is going to be in general a function of the position x and time. So that's what makes it dynamic. So for this problem, one way to sort of simulate this is forget about the ball or the object itself, but just try to approximate what is the load that it applies to this beam. And there are obviously many different ways of doing this, but one crude approximation is that this function, this force P that it applies on this beam, can be represented with this sort of a function. So you can imagine if the object is a little bit flexible when it hits the beam, the object will compress a little bit and then bounce back. So this entire time, would be the time of contact between the object and the beam. And since you are applying a time varying load, then again the beam is going to oscillate uh, mm, and the wave might be propagating along the length of the beam. So these are the governing equations and the boundary conditions for a structural or solid dynamics problem. Okay, and now all we are going to do is take this equation, follow our steps of the finite element formulation, and let's see what happens. So we take the governing equation, we've just shifted this to other side, we have a minus sign there, and multiply it with a virtual displacement, do integration by parts, and what we get is the same old thing that we had before, except this term. So this term is coming due to the inertia effects in dynamics. This term is coming from u bar times rho u double dot. That's right here. U bar dot with divergence of sigma, that leads to this term. This term was the internal virtual work like we had before. What is left is u bar times b, which is the external force, and some boundary terms. Those boundary terms came from the integration by parts of this div sigma. So this plus this was what we got from the integration by parts. So the only new term here is this term. Yeah. No. So this is an equation that is going to hold at every location and at all instants. So the way that this term comes about is actually, if you want to write it in terms of a time integral, then we have to go back to Hamilton's principle. That is something that we talked about when we were talking about variational methods, energy methods. So you can derive this equation of motion using Hamilton's principle, and in that principle you have integrals with respect to time. But here we are assuming that this equation is going to hold at every location and at every time instant. So at a given time, this equation must hold. So what we are doing essentially is we are saying that we are going to solve for u along x and in time, but for a given time t, this equation must hold for all times. So essentially that you will see that what we will get after the finite element discretization and all that will be an ordinary differential equation as opposed to a kd minus f. So this equation is it has to be enforced at every time instant. So all right, so this is the new term that we have here, and what we'll do now after integration by parts is discretize our domain. So any integral over the domain is equal to sum of integrals over the elements. That's just discretization. And the next step is finite element approximation. We use the same approximation. U displacement is equal to n shape function matrix times degrees of freedom. The only difference here is that this displacement is a function of x and time. But the shape function matrix, that's the same old shape function matrix that we had before. But now the degrees of freedom of any element are a function of time. So you can imagine if I have some cantilever domain and it has been discretized with finite elements, there's lots of degrees of freedom. If I pluck it and let it oscillate, every degree of freedom will depend upon time. So time dependence of the problem is completely captured by this variable d. And the same old formulas that we had before, strain and stress. So actually this should be a vector, stress vector, not a stress tensor, according to the Voigt notation. So we have the same thing, B matrix times D and dB times D for the stress and the strain. The only difference again is that all these things are time dependent. These terms are not time dependent, but the result is obviously time and space dependent. So one consequence of using this finite element approximation is that when you take the derivative of u, that's the velocity, you take another derivative of u, that is acceleration. if you just differentiate this equation with respect to time twice, what you will see is that u double dot, that is acceleration, can be written as the same n matrix times degrees of the second derivative of the degrees of freedom. Because the degrees of freedom are functions of time now, therefore this thing is like the nodal acceleration. Instead of nodal displacements, these are nodal accelerations. So if you plug all these approximations back into the weak form, what you will see is that you get the same old thing, B transpose dB, that is our k element, N transpose B, that was our force element force vector, and N transpose traction. So all this was what we had before. All this was what we had before. The only new thing is coming from this term. You can plug in u is equal to n times d, and u double dot is equal to n times d double dot. And if you do that in here, what you will get is n transpose n and the nodal acceleration vector. And this matrix is called the mass matrix. So this might not be something that you have seen before. How many of you have taken the structural dynamics course? So is this something that you saw before, somewhat? I think actually in most of the structural dynamics courses, what people do is use a lumped mass matrix. So in a lumped mass matrix, if you have a beam element or any type of element, you shift half the mass here, and that's lumping. And what that creates is a diagonal mass matrix. But if you go strictly by the formulation, strictly by the finite element formulation, what you will get is called a consistent mass matrix. So this matrix right here is called the consistent mass matrix, and this in general is not diagonal. Okay. So what you will, so finally what you can do is assemble all the element equations, and you will see that the equation of motion just becomes a vector equation now, where you have the mass matrix times acceleration plus stiffness matrix times nodal displacements minus applied forces is 0. This is the equation of motion that we are trying to enforce at every time. At any time, this equation must hold. Okay, so now this formulation is also called a semi-discrete formulation. And the reason is that what we have done till now is discretized our problem in space with finite elements. We still have a continuous problem in time. So it is semi-discrete. It is not fully discrete. So, and another point to note here is that this system of equations, this is a second order ordinary differential equations, system of ordinary differential equations. So let me ask you this. Would this equation be an ordinary differential equation or a partial differential equation? So this is a time-dependent partial differential equation, because all these derivative operators, they are with respect to space variables, x, y, z, and all that. Divergence is with respect to x, y, z. And there is, in addition, there is a time derivative sitting in there. So these are all partial derivatives. When we use the finite element formulation, we convert these partial differential equations to a system of algebraic equations. When what we did before was we converted that partial differential equation to kd minus f. That was a system of algebraic equations, simultaneous linear equations. But now with dynamics, all that we have is this extra term, which makes this system of ordinary differential equations. Each row of this system, this is a matrix times a vector, matrix times a vector, and all that. So each row of that has a double time derivative in there. So it is an ordinary differential equation. So this is the, hopefully you are familiar with this equation of motion. You might have seen this before in different forms. And what sometimes people do is they add some physical damping. But this is, again, this is some sort of an artificial physical damping. There's not much realistic basis to this. What people do is they say that there is a damping matrix, which is a linear combination of mass and stiffness. So if you do that, the damping is proportional to the velocity. So governing equation of motion for this model, for the finite element model, turns out to be this. Um, all right, so in the end, what we have to do is we have to solve this ordinary system of ordinary differential equations. And to do that, we will have to do some sort of a time integration. Um, so since this is a second order ordinary differential equation, let's take a look at a simpler case for first order differential equation. You have a question? Yep. Mm-hmm. Right. 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 So all these terms, after you have discretized and integrated over the elements, these are all constant matrices, right? K is a constant matrix, M is a constant matrix, so it is just numbers. So it's there's no x dependence in this equation. So what we had earlier, we get kd minus f, right? So kd minus f doesn't have any x terms sitting in there. It's just nodal degrees of freedom multiplied with a k matrix. So the same thing happens here. You have this M matrix with nodal accelerations. These accelerations are dependent upon time. This displacement is dependent upon time. The load can obviously be time varying. So this equation is a system of second order ordinary differential equations. And does anybody know, I guess, if you've taken any course maybe in second year or third year undergraduate about how to solve ordinary differential equations with numerical methods? So maybe this is familiar to some of you, but um, but let's first take a look at a simpler problem, which is first order ordinary differential equation. So this problem is of a transient heat conduction, and this also we have done before, except that what we had before was just this term. Divergence of the heat flux is equal to uh, so divergence of this heat flux vector is equal to heat source at every point in the domain. So the idea is that you could apply, you have a plate and you have some temperature and some heat source that is being applied to this plate. The temperature isn't going to go to its final state right away. It is going to take some time, and then it will reach a steady state. So the time that it takes to reach the steady state, in that time, the solution is called transient. So that's why we have this transient heat conduction. Yes. Theta dot is the time rate of change of temperature. Theta is temperature, temperature at any point in the body. Rho is the density of the material. C is the specific heat capacity of the material. So this governing equation basically governs how the temperature is going to vary at any point in this domain. And all these things we have seen before. This is the constitutive law, temperature boundary condition, and heat flux boundary condition. So if you take this and again take this governing equation multiplied with a virtual temperature, do your integration by parts, discretize, and then use finite element approximation. I'm skipping all those steps. What you will get is something similar to your equation of motion, where this is a heat capacity matrix, just like a mass matrix. This is a heat capacity matrix times. Now the degrees of freedom are temperatures here. So, but there is only a single dot, which means it's a first order ordinary differential equation. This is conductivity matrix, and this is the heat source. So essentially, we have to solve this equation for every time. At all times, this equation must hold. And the form of this heat capacity matrix is very similar to our mass matrix. Instead of rho n transpose n, we have rho c times n transpose n. This is also the consistent heat capacity matrix. All right. So how do we solve a first order ordinary differential equation. So the idea is that you have some variable d, which is a function of time. In general, its curve could be looking like this black curve right here. So obviously, it's varying with time. And the idea behind time integration is that if you give me an initial moment at which I know the state of the system. So let's say that state is Tn, some general time n. I know the state of the system. I know where it begins from. If I know where it begins from, I have to somehow calculate where it goes after a small time delta t. So using the information at time step n, I need to find out where it goes to at time tn plus 1. And the idea is that since I know the value of the temperature at this point, I know the rate of change of temperature at this point. I can, using this information, I can calculate where it will go. So, so in this case, what I'm showing you with the blue line is what is called some average measure of the rate of change of temperature. If d was displacement, v would be velocity, right? But here d is temperature, so v represents rate of change of temperature. And we are denoting all these quantities with at different times with these subscripts. So dn is an approximation for the value at n, vn, and similarly at n plus 1. But so one common method that people use to integrate first order systems is called the Euler method. Has anybody seen this before? Euler's method? Not many, okay. So we have this, the idea is that we are going to approximate the derivative with respect from n to n plus 1 with this quantity vn plus alpha. This vn plus alpha could be some linear combination of the derivative at n and the derivative at n plus 1. So you can see that the slope here and the slope here, this line has somewhat of an intermediate slope between these two. So, so that's what this equation says, the first equation. Vn plus alpha is a linear combination, 1 minus alpha times and alpha of Vn and Vn plus 1. So this is Vn, this is Vn plus 1. So this is the first equation that the Euler's method states. And the second equation says basically that you can find out dn plus 1, that is the state at n plus 1, by taking dn right here plus delta t times the slope. So this is what we are saying here is you can extend this line and the approximate solution at n plus 1 is going to be this dn plus 1. So you can clearly see that all these methods of time integration, they are going to make this much error. No matter what time integration scheme you use, there will be error. And not only will there be an error, that error will accumulate over every time step. If you have, let's say, if you are simulating something for 10 minutes, and if your time step is 1 second, then there's 600 seconds in those 10 minutes. For each one of those 600 time steps, you will make this small error, and that small error will keep on accumulating. Okay. So what I've shown you here, in this case, what I'm using is that Vn plus alpha is equal to Vn. So what I'm using is alpha equal to 0. So if you use alpha equal to 0, it will predict that my next state is going to be here. And then you repeat the process here. You say that from here I will go to here, and then here. So you can clearly see that the error will keep on growing. If you want to reduce the error, you reduce the time step. Okay. So some of the common methods in this case, what I've shown you here is with alpha equal to 0. This is called the forward Euler method. Yeah. So sometimes that can happen. But for parabolic problems, basically this heat conduction problem is a parabolic problem, meaning that it approaches a certain steady state. So these errors in general don't cancel out. There is some sort of a drift usually. So, but you have touched on something that you can see here. The slope here is much greater than the actual slope. The slope here is much smaller than the actual slope. So if you take a combination of those two, which is what the midpoint rule does, that midpoint rule actually is much more accurate than either forward Euler or backward Euler. And the order of accuracy, maybe you can just take a extra note here, that for the order of accuracy for this midpoint rule, which is also called the trapezoidal rule or the Crank-Nicolson method, the order of accuracy for this is 2. Just like our order h square, in this case it is order delta t square. Yeah. You don't know the slope for Tn plus 1. So what you will do is, yeah, I'll show you that in a minute. So you're solving for both the slope and the value at Tn plus 1. Okay. So in these two equations, this is unknown, Dn plus 1, and Vn plus 1. This is unknown. We have two unknowns here. But if you take these two equations and substitute it into our governing equations, this is the governing equation, we'll write this at Tn plus 1. We know that this equation holds at Tn. We are trying to go to Tn plus 1. So we'll write this equation at Tn plus 1. What we have is this. There are two unknowns in there. Now if you just substitute for Vn plus 1 from this equation and for Dn plus 1 from this equation, you can write it out in this way. And the only unknown here is this Vn plus 1. So this is a matrix times a vector is equal to another vector. So you know the load slash heat source at n plus 1. You know the conductivity matrix. You know the current temperature, and you know the current temperature gradient. So the entire right hand side is known to you. And this is something very similar to your Kd is equal to F. Instead of K, you have some general matrix times a vector is equal to another vector. So you can solve this equation for V. And so once you solve this for V, you can go back and plug that into the first equation. You can get Vn plus alpha, and you can take that Vn plus alpha here and solve for Dn plus 1. So the idea is that using the state at here, at this point, we had D, the temperature, and the temperature rate of change of temperature at Dn, at Tn. Using that information, we have marched to this new time, and you can keep on repeating that process. So, but again, the important thing to keep in mind is that there will be errors. In general, this method is the second order accurate method. So what it means is that if you decrease delta t by half, your error will go down by 4 times if it is a second order accurate method. So this is sort of the idea behind time integration. The entire thing is, you know the solution at some Tn. Knowing the solution at Tn, you are going to advance the solution to Tn plus 1. And that's what we do in dynamics also. So, so time integration for structural dynamics, if you recall, what we just did right now is that this was the equation of motion that we got from the finite element formulation. Now, since this is a second order equation, one way to solve this is split it into two first order equations. Do you remember how to do that? If you have a second order ordinary differential equation, you can always make it a system of two first order equations. And so what we are just doing is defining a new variable, velocity is equal to time derivative of displacements, and time derivative of velocity is acceleration. So we have the same equation again, mass times acceleration and all that. So this is the system of first order equations, but what is the problem with this? And since now we have the first order equations, we can use Euler method to solve it or some other first order methods. But the problem with this method of going this route is that you have just doubled the equations. So imagine if you have this finite element equation and you have 1,000,000 degrees of freedom, you have immediately doubled your degrees of freedom to 2,000,000 now. So this is in general not a very efficient approach. So what we do normally in structural dynamics or solid dynamics is we use this Newmark family of integrators. So this Newmark family of integrators, what it allows you to do is actually integrate this second order equation directly. And let's see how that works. So again, the approximations that we use is that accelerations will denoted by a, velocity, and displacements. These are approximations for the value at Tn. So for example, here, this is the value at Tn. We know the state at Tn. We know displacements, velocities, and acceleration at n. Using this information, we have to go to n plus 1. So the Newmark scheme, what that assumes is that these two equations, these are the two equations that it uses to approximate the derivatives. Just like in your Euler method, we approximated the derivative with Vn plus alpha. Here we are going to approximate the accelerations as An plus gamma. So the two parameters for this method are gamma and beta, and this was originally when Newmark developed it, this was called the beta method. Or so there are these two parameters, gamma and beta. In general, we use the value for gamma equal to half. So again, we are saying that the velocity is old velocity plus delta t times some acceleration. And displacement is, so this is hopefully something that you recall from maybe dynamics from the second year, where you have V2 is equal to V1 plus delta t times acceleration, right? And this is D2 is equal to D1 plus t times V1 plus half acceleration times square, half AT square, right? So this is also acceleration, some sort of an effective acceleration. And when you when you use these two approximations and plug them back into the governing equation, you can write by rearranging terms. There's nothing in there, just algebra, that some matrix, where this is the mass matrix, damping matrix, stiffness matrix, all this thing you know. So this would be a one matrix times a vector is equal to some right-hand side vector. That's what basically, at the end of the day, for any type of problem that you want to solve with a computer, you have to end up with a system of linear equations. So this is a matrix times a vector is equal to another vector. And everything on the right-hand side, you know. Velocity at n, you know. Acceleration at n, you know. Displacement at n, you know. And using this information, you can go and calculate an plus 1. So you know an plus 1. And then you can go back to these equations 1 and 2, calculate Vn plus 1 and Dn plus 1. So essentially what you've done is taken this state and time stepped to n plus 1. And once again, you will make errors when you do this time stepping, and errors at every time step. So, so some of the common methods that people use in structural mechanics, for those two parameters, gamma and beta, that we had, Newmark parameters, one method is this central difference method. And this is what is called an explicit method. And this is also the basis for abacus explicit. So you might have been working with abacus standard, right? And you've seen that there's another way of analysis that is called abacus explicit. And what this abacus explicit uses is this central difference method. And the good thing about this method is that this is explicit. What does that mean? It means that uh, if if gamma is half and beta is 0, then this term goes away. And if C matrix is diagonal and M matrix is diagonal, then the matrix equation that I have is a diagonal matrix equation. So I don't have to solve any equations. And that is in general true for all types of explicit methods. If you have to solve a system of equations, that method becomes an implicit method. If you don't have to solve a system of equations, or if your system of equations is a diagonal matrix, that type of system is called explicit. So explicit methods are very easy to solve, but the problem with those methods is that you cannot take a big time step. So just like here, if I have this structure, if I drop a ball on this and I'm going to try to find out how this oscillates, I cannot use some big time step. I need to take very small time steps and try to figure out how this thing oscillates. And that time step is given by this limit where this omega is the eigenvalue of the entire mesh. So, but what you can keep in mind is that there is this limit for abacus explicit or general explicit methods to be stable. But when you use abacus explicit, you may not have to worry about what this delta t is, because abacus will automatically try to calculate what is this quantity, and it will choose a time step that is smaller than this. So another benefit of using this abacus explicit instead of abacus standard is that, let's say you have some structure and you apply some load, a static problem, not a dynamic problem. You apply some load and you will get some static solution. So what abacus explicit will do is it will try to solve this problem in a dynamic way, but it will add damping to the thing. So what will happen is you apply a load and it will oscillate and go to a damp out the oscillations. So it will calculate, or it will converge to the static solution. So that's what this central difference explicit method does, and that's what abacus uses for this. But for high-rise buildings or for general civil engineering problems, what we use is an implicit method. And the reason that we use implicit method is because we want to take very large time steps, because we are not interested in how the small oscillations of the building are taking place. We are interested in the first few mode shapes. So if you have a tall building, you are interested in the main mode shapes of the building. So you're not interested in the small oscillations of individual beams and columns, but what you are interested in is the main mode shapes. So you use very large time steps. And since this method is unconditionally stable for any time step you use, so this is again a very what this means is it doesn't matter how big a time step you choose here. This method will not give you an infinite solution. So obviously, if you use a very big time step, your accuracy may be very bad, but you will still be stable. Okay. And then there is this third type of method where you choose a different value of beta. This is called linear average acceleration. This is also implicit, but it is not unconditionally stable. So mostly people use either this central difference or this trapezoidal rule. So that's basically what we have in what is going on behind dynamics. And as you can see, there's not much to dynamics if you know the finite element formulation. The only thing that comes in extra is this mass matrix and some time stepping algorithms. So solving dynamic problems with finite elements is not that much more complicated than your regular finite elements. So all right. Let me just very briefly talk about this nonlinear problems. So the idea is for nonlinear problems in structural and solid mechanics is that nonlinearity usually stems from these two sources. One is called a material nonlinearity, and for example, if you have steel, if you do a uniaxial tension test, you will see that after hitting a certain point, it will start to yield. So those types of materials can be described well with a plasticity theory, and those are nonlinear materials. Okay, but as opposed to nonlinear material behavior, you can also have geometric nonlinearity. And commonly in civil engineering or structural engineering, we refer to this as the P delta effect. And what does that mean? If you have a column with some sort of an eccentric load, you design that column for the moment that is produced due to that eccentricity. Let's say if this problem was linear. Let's say if this problem was linear, or our model was linear, if you apply a load P, and you measure what deflection you get after applying this load. If you double the load, you will get twice the deflection. That's the linear problem. But for nonlinear problems, you can see that this type of a column, after a certain load, it will buckle and it will have instabilities. So I don't know if anybody here is taking a course on stability of structures. So those, all that formulation depends upon these second order effects. You have to consider geometric nonlinearity in order to consider stability of structures. So those are problems with geometric nonlinearity. And essentially what we are doing is, we are considering this strain that we had for linear problems. We had left out this strain. So this was our linearized strain. If you add the component of if you take the full Lagrangian strain, then those problems are called geometrically nonlinear. So the most common way of solving these nonlinear problems is the Newton's method. And just to give you an idea of what this Newton method does is, we'll consider this single degree of freedom, just one spring, but that spring does not have a constant K. That K depends, the stiffness of the spring depends upon the actual displacement. So let's say that the spring behavior is something like this. If I stretch the spring by U, the stiffness will increase. So if the spring is linear, then we get this line, K naught times U, right? If the spring is nonlinear, let's say it is nonlinear with respect to U cube, then as you stretch the spring, its stiffness increases. And similarly in the opposite direction also. So what this is measuring is the spring force with respect to displacement. So clearly this is nonlinear. And now if I apply a load P, the equation of equilibrium says that internal force minus external force has to be equal to 0. For this point, if you just write out sum of forces in the x is 0, you will get this. So essentially what we are trying to do is find the value of U for which this equation is 0. That's solving a nonlinear problem. Okay, and the way we do that is, these are some of the steps of this method. So let's go through this thing. The first thing that you do for a nonlinear problem is you assume a solution. What solution should we assume? Any solution. Any solution you can assume within the radius of convergence. So for example, if you assume that I apply a load P and the spring is not going to deform, zero displacement. Let's say I chose that as an assumption. So what I'm saying is, I will choose this point as my first guess. And the next step is that I will find the value of this GU at this point. If this is close to 0, then I'll say that this is the solution. If this is not close to 0, then I'll try to find what is the derivative of this function at this point. So this derivative, this is dg over du. That's the slope of this line. I can calculate that at this point, and according to this derivative, it will predict that your solution is somewhere here. right? Now I will calculate my function value again. But obviously g is not 0. So it says, well, I need to repeat that process. I will calculate my derivative again. And it will say that my next solution, or like my next guess is here. And now I will use this, I will calculate g again at this point. It's not 0. And I'll calculate the derivative again. So you can see that uh, progressively your approximations are getting better and better towards the actual solution. So this is what happens in Newton's method. So this is basically the most common way of solving these types of nonlinear problems. In general, since this was a single degree of freedom problem, in general you could actually have something like this. So this is again a two-dimensional beam. This is from my code. I haven't given you this code, but this code, this one can take large deformations. So the important things to note here are that the governing equation, this equation holds on the deformed configuration. And this equation, governing equation, can be written on the original configuration by slightly modifying it. So there is a difference between this divergence and this divergence. This divergence is with respect to the modified due to the new configuration. This divergence is with respect to the old configuration. So this problem is basically applying an end moment to a cantilever beam, and it should completely circle, become into a circle, or if you keep on increasing the moment, it will keep on wrapping around itself. But for these problems also, what we do is pretty much the same thing. Take our governing equation, multiply it with virtual displacement, but this integral needs to be done on the deformed configuration. So the most important step for this is that you can modify this integral to, or you can transform this integral back to the original configuration. This was the deformed configuration. This is the original configuration. All I'm doing is transferring this integral back to the original configuration. And this is this J that is very similar to your isoparametric map. So this is again something, if you can understand isoparametric map, you can understand large deformation. So we'll go over this maybe a little bit after the lecture on Friday. But I hope you can take a look at some of the capabilities of Abacus for dynamics and for nonlinear problems. So we'll see you on Friday in Armstrong building.